from the RSNA. This is the Radiology Artificial Intelligence Podcast. My name is Paul Yi, and I'm a radiologist at the University of Maryland and co-host of the podcast.
And my name is Tejani, and I'm a radiology resident at the University of Texas Southwestern Medical Center and co-host of the podcast. Each month, we dive into the hottest topics in radiology AI and talk with leading experts, thought leaders, and movers and shakers in the field.
For the month of September, we take a closer look at the latest Muppet taking over NLP in radiology, BERT. Radiology Artificial Intelligence authors, Drs Jae Ho Sohn, and my podcast co-host, Dr. Ali Tejani, join us for a conversation about NLP and transformer-based models in the context of their research. Dr. Jae Ho Sohn is an assistant professor of radiology at UCSF, where he leads the Big Data in Radiology, or BD-RAD research group, which has an active NLP research program based at the UCSF Center for Intelligent Imaging. Dr. Ali Tejani is a PGY3 radiology resident at the University of Texas Southwestern Medical Center and deputy editor of the podcast.
This is an exciting topic, especially considering the recent back-to-back publications in radiology artificial intelligence, showing the breadth of NLP use cases in radiology. We hope this conversation catches your attention. Sit back, relax, and enjoy another episode from the Radiology AI Podcast.
Ali and Jay, thanks so much for joining us here on the Radiology Artificial Intelligence Podcast. It's really great to have you both. I'm Ali as my co-host and Jay as esteemed special guest. And I'm really excited to talk to you both tonight about natural language processing, BERT, and all of these other really interesting topics around the topic.
Thank you for the invitation.
It's great to be here.
Jay and Ali, both of you have really interesting backgrounds. You're both physicians, both radiologists, both AI researchers, and at different stages of your career. And I'm always really intrigued by how people got into AI, and in particular, their specific fields of study, in this case, NLP. So can you share with us and our listeners about what got you into AI, what your background is, and more specifically, how did you get interested in NLP and BERT models?
So at Hopkins, I studied mathematics and statistics as my undergrad and master's degree at Johns Hopkins. And there I met my mentor, Dr. Tilak Ratnanathan, who's a mathematician who's applying mathematical techniques to study the brain. And I was really impressed by his work. And he's actually doing a lot of computer vision work at that time. This is before the era of deep learning. So already primed with that interest, I entered medical school and had these vague ideas of applying mathematics to medicine. And then around 2014, 2015, I learned that the deep learning algorithm had made a big breakthrough. And I came to the Bay Area for my intern year and residency. And I was actually able to join a study group that was run by Google Photos team. That was really interesting experience. And there I learned some of the earlier models of convolutional neural network and how to apply these techniques. So naturally, being in medicine, I took those techniques and started applying. I became really, really interested and started forming a lab and forming a group. So that's how I came to where I am.
That's inspiring, and I don't think my history will line up too well. Unfortunately, it's a bit of a non-traditional story on my end. In undergrad, I studied political science and actually journalism, and so my trajectory was a bit different, and I always loved being able to communicate tough information, more specialized concepts, and converting it to layman's terms, right? Making it relatable and understandable. Long story short, I did find my way back to medical school, and I was in the reading room on one of my medical student radiology rotations at the University of Texas Southwestern Medical Center in Dallas, Texas. And we had conversations about AI. This is back in 2016, around the same time Jeff Hinton had said we should stop training radiologists. And I was falling in love with radiology, right? I'm seeing it. I'm in the reading room. I'm falling in love with this profession and the nuance and the detail and the workflow. And fortunately, I came across several mentors at the time. Dr. Julia Fielding was our body division chief, and we had some fantastic faculty, Dr. Yang and Dr. Jesse Ryan, who took me in and mentored me in imaging AI, computer vision models, NLP. And we formed a pseudo lab group and worked our way through just interesting use cases and trying to identify clinical questions and proposing solutions. And so as I went into residency at UT Southwestern, I continued working with them, and they continued to train me, and in the addition with Dr. Travis Browning and Ron Pishock with imaging, Dr. Alan Pishock with the Imaging Informatics Division. And we started finding more use cases for BERT specifically. And we found that BERT is a tool that can really help us improve the way we deliver care, essentially, at the end of the day. Now, for me, though, I still love journalism and communication. And so the way I kind of imagine this is one day we can have maybe explainable AI, right? AI that we can translate from the technical terms, the jargon, to those who may not be as savvy with the technicalities, physicians, patients, other clinical interested parties. So we'll see what the future has to hold, but hoping to continue working with AI in the same vein.
That's fantastic. Thanks both for sharing your backgrounds and a little bit about your journeys here. I want to start out with one clarifying question about natural language processing, because I think that, when I initially heard about NLP and started learning about it, I assumed it's all machine learning in the sort of way that we kind of think about it, specifically with regards to deep learning. But as I learned more about it, it dawned on me that a lot of these NLP tools, even used in 2022, may not actually involve machine learning, at least in the way that a lot of people think about it. Can you guys give us an overview of NLP, what that means, and how related or how inclusive of it is it related to deep learning and machine learning?
Yeah, so I think NLP probably benefited the most from machine learning. And that's probably why a lot of people see NLP as part of machine learning subfield. But you're right that I see NLP as something that's separate, and it has a lot of relationship with machine learning for sure. So natural language processing is a group of techniques used to process texts. And sometimes it can involve classification. Sometimes it can involve automatic generation of text, summarization, topic modeling. There's many different subfields within natural language processing. And naturally, for classification tasks or certain generative tasks, machine learning can become quite relevant. And if you think about where deep learning came into play in the context of natural language processing, it actually even predates the times of computer vision. And one of the most successful applications of deep learning or convolutional neural networks or various types of neural networks was first in natural language processing and then moved forward to computer vision. So very long, tight relationship, but sometimes a little bit different. And I can give you just some examples. Certain regular expressions that you're used to select certain texts within natural language processing may have nothing to do with machine learning. But it's really important for certain types of natural language processing tasks, and especially in radiology, where we speak a fewer number of words and certain ways of speaking in radiology or certain ways of communicating in radiology, oftentimes lend itself really well to regular expressions. So in those cases, machine learning might not be as relevant.
And what really fascinates me about NLP is how long it's really been around. If you take a look at some of the more original, what we call classic, I like to say old school natural language processing models, you think about the bag of words model. That's a term people may hear. That dates back to the 1950s, 1960s. It's quite old. It's been around for a while. And as you follow it through, you start seeing this development. You see multitask learning, seek to seek, word embeddings, and all of a sudden you start transitioning to word to vec and transformers, and you start hearing Sesame Street characters like Elmo and Bert. And so that's happening over the last 20, 30 years. And I think what essentially NLP has seen is an attempt to capture the complexity of human language. And we've gone from, I think, more context independent methods to those that actually take context into play. And that's what BERT actually is. It takes into consideration sentences that border a target area, words that aren't necessarily in sequence in the left to right that we think about, but maybe preceding or instead of just following a word. So long story short, I think we're seeing this progression to robust models and robust methods that do work in tandem with neural networks, as Jay was mentioning.
Yeah, that's really interesting. And speaking of context, both of you have recently authored separate original scientific articles in the journal using BERT. Jae Ho, you've senior authored a paper using BERT for detection of speech recognition errors, things like dropped words or repeated words. And Ali, you've done the same, but for a slightly different task, which is actually finding some type of annotations for different support devices on, I believe it was chest x-rays. So can you describe to our listeners what is a BERT or a transformer model, and how is it relevant for NLP tasks, and in particular for radiology?
BERT is a transformer-based natural language processing approach. I wouldn't say that I go into all the theoretical depths of how BERT was made, but some key components of what makes BERT particularly powerful is because of its structures and its approach, it allows pre-training and fine-tuning at a level that was not seen before that era. So as Ali had mentioned, bag of words, and there was word2vec and its related models. Up until that time, I think one of the key limitations of NLP was that there is no great pre-training method as the one that exists in the world of computer vision, such as ImageNet-based pre-trainings. And BERT allowed these models to capture train from a very large corpus of unlabeled data and retain that information and apply them into new tasks and maintain its accuracy. So I think that was something that was really important for BERT. And maybe I'll stop here for comments from Ali as well.
No, you're the expert, Jay. So, BERT is a large neural language model, and we saw that it has improved performance over the more traditional natural language processing models that we talked about. But these benefits definitely came at a cost, quite literally a financial cost. It's a very expensive model to train at baseline. It takes a large amount of compute. As Jay alluded to, it's pre-trained on a large corpus. And so you can imagine the time that it takes to really develop that robust model. And so what we have BERT. It's so exciting though, because in the last few years, we're seeing all these offshoots from BERT, these new domain specific models like PubMed BERT, right? Training BERT on, I think it's 14 million abstracts, like 3 billion words. But now what you have is this pre-trained model, this pre-trained BERT that you can take and fine tune to medical tasks, essentially, things that leverage that medical knowledge contained in PubMed BERT. And what we're starting to see that those pre-trained models offer more domain-specific improvements in performance, but also they're more usable in a way. They require less time to train. You're really just, like Jay said, you're fine-tuning them instead of pre-training a model from scratch. There's a less of a demand in terms of the training, the number of cases required to train it. And that's kind of what our paper was touching on too, is this offers a whole new opportunity for resource-constrained labs, hospitals, institutions, or anyone that really has a limited amount of data, a limited amount of time and cost, finances. So it's an exciting field. We're talking just earlier today, even in the reading room, about BI-RADS BERT. There's a BI-RADS BERT, there's a RAD BERT, there's a BioBERT, PubMed BERT. So we're seeing all kinds of offshoots just within medicine and radiology itself now.
Yeah, this is super interesting. I like all of these different acronyms: BERT, PubMed BERT, Distill BERT, Roberta, and DeBerta. So amidst all of these different so-called foundation models or kind of pre-training corpuses, what are some of the benefits offered by this technique? We've seen it pretty clearly, I think, with ImageNet pre-trained models, and most recently with this RAD ImageNet that was published in our journal. But one of the interesting findings from your paper, Ali, was that it seemed like some of the models, like DeBerta, actually show the highest performance with using far fewer reports than some of the larger data sets. So to me, that sounds counterintuitive, and I don't know if you have any thoughts or insights into why using fewer reports might actually yield a higher performance. And so any comments about pre-training and maybe uncovering some of those nuances would be great.
Sure thing. And so don't ask me why we name these models the way we do. I'm still trying to figure that out. I get the Elmo and I get the BERT, but when we get to Roberta and Distilbert and DiBerta, I'm sure it comes down to the architecture, and Jay may actually know more about this than I do. But that was actually the point of our study, was to see, well, how much data is really needed to maintain performance before we start seeing it drop. And we took a look at BERT, of course, PubMed BERT, because we're interested in biomedical literature and having the specific corpus guiding our pre-training. But then Roberta, Distilbert, and DiBerta were newer models that had recently been introduced at the time. And though we don't have to get into the technical details, the architecture essentially was a variance from the BERT architecture. And when it comes down to it, it really depends on the parameter count. And if you take a look at Roberta, Distilbert, and DiBerta, you see that DiBerta actually has the highest parameter count. It's almost 435 million. Now, if you compare that to BERT and PubMed BERT, that's at 109, 110 million. So that may be a possible explanation for why we saw it maintain performance even at smaller data set sizes. That being said, though, PubMed BERT was consistently a high-performing model even as we decreased training set size. And for context, we actually looked at performance of these models in identifying 4 different support devices on chest radiograph reports specifically: endotracheal tubes, NG tubes, central venous lines or catheters, and Swan-Ganz catheters. Now, Swan-Ganz catheters were relatively underrepresented in the data set. And so what we saw is that the models all had some trouble, relatively speaking, in appropriately annotating that finding. But PubMed BERT still maintained its performance, whereas DiBerta actually demonstrated weaker performance at that point. So it's interesting. There are a lot of unanswered questions here that we still have to look into. But I think to answer your original question, the parameter count may offer some insight into why we still saw relatively high performance at even smaller training data sets. Jay, I don't know if you had any thoughts on there too, or if you've worked with these models as well.
Right. There's many different variations that I certainly cannot keep up with all the different variations and the names, but I think it all comes down to a certain change in architecture of the transformers, the attention mechanism, and certain changes in performance that results from it for certain subtasks. So for the BERT models, you could change the underlying pre-training task or the architecture or the attention mechanism in order to improve its performance for various different tasks. And as you know, a lot of how deep learning works, and including BERT, it's empirical. So we don't necessarily always know why it's working better, but we can make some educated guesses. Sometimes I'm sure it depends on the particular subtask that you're working with. And if the original data set that was trained on was somehow similar or had some relevance to it, it could be helpful. Sometimes certain architectures could match better for that particular task. So I think those are my thoughts.
Yeah, that's really interesting. Speaking of the parameters, the number of parameters and the size of the models, I think one concern is always, without a lot of data, which may be mitigated by having pre-training, there's the concern that there might be overfitting or essentially memorizing of the data. But I wonder, in the context of radiology reports where, as you've mentioned, Jay, there's only so many ways you can really say that there is or is not cardiomegaly, there is or is not maybe an endotracheal tube. I wonder if that might not be such a bad thing. Let's say that you're trying to develop an NLP model specific for, let's say, Hospital X, and Hospital X has 20 radiologists, and these 20 radiologists happen to dictate in a very predictable way. And that might sound a little bit like heresy with regards to generalizability with machine learning. I don't know. I'm just thinking out loud. What do you guys think about that possibility?
Yeah, I think certainly generalizability is key sort of a challenge in deep learning, and also key thing that deep learning broke through and allowed better performance. So I think having diversity of data sets is certainly really important, and good regularization. So for our cases with the speech recognition error detection, we worked with the reports from, I believe, over 120 different radiologists, and also from 2 different hospitals. So that lends itself to a little bit more diverse data set. I think that allowed the model to perform better and generalize better in certain other tasks. And on top of that, we always want to think about regularization to reduce overfitting. those two are my strategies usually to improve generalizability.
And Jay, I actually have a question for you. I love that paper. It was so exciting to see, because at that time, I think that was the first paper that had come out in radiology, or at least in a radiology specific journal. Don't quote me on that, but I think it was. I remember being just so excited to see this use case. And I have a burning question, Jay.
Oh, yeah.
Are you and your team using this tool now in practice, or have you tried looking at maybe deploying a pilot project where you're actually seeing if we can detect these errors in radiology reports and actually suggesting those changes? Because I think it's a really high value use case.
Yes.
I absolutely love it. What are your thoughts?
Right.
Yeah.
We are very, very excited to use this technology. I think to integrate this into like immediate day-to-day workflow, which was the intended purpose. So let me just take a step back. So this algorithm that we're talking about, speech recognition error detection algorithm for radiology reports, it's intended to work sort of alongside the radiologist. And when the radiologist dictates a sentence that appears to be somewhat off and possibly containing error, it's supposed to raise red flag and say, oh, take a look one more time because the model thinks there may be an error. So ideally, it's actually running in sync with the radiologist at that spot. Unfortunately, there's some technical challenges of doing that in real time. There's more effort, and we hope that it gets integrated either natively through these dictation software or in radiology workflow. But we actually, as part of the paper, did work with real-time prospective clinical data set. So was it four radiologists started dictating reports. And then as soon as they see potential errors, they actually screen captured and then sent it over to the model to see, is this model working okay or is this not working? So I know that's not the most convenient workflow, but at least tested to see, is this model actually going to work if it were to be integrated into workflow and if informatics and software engineering allows it. And I think that was really useful sort of revelation, and it worked actually much better than what we expected. So that's sort of where we are. Hopefully in the near future, we can actually integrate this into our workflow.
No, that's absolutely exciting. Again, I think that even having something available to test run and see actually how it fits into the, like you mentioned, the kind of the infrastructure supported by the informatics of the software engineering team is so important, right? And I could even see this just starting out with just laterality, right? Just having a quick check at the end of your reports, which I think, I've seen variations of it, just having a quick check on left versus right. I've been there, done that. I've made that mistake too, and having that sort of tool could be very helpful. And maybe that's a smaller scope use case for these BERT-based models.
I think one advantage of NLP is that it's a little bit easier to integrate than certain computer vision models in radiology that may require sending large image files to a different server that processes the image. You can just have like a web window open on the side or some other small text program that can run along the side. So that's one advantage to easily test these algorithms. We actually have like a Python as platform website that allows you to put in these sentences and then check, is there an error or not? Now, to integrate that into the hospital system, of course, requires some regulatory steps and other things. So hopefully in the near future, we can get that done.
So it's interesting that you mentioned these regulatory steps and these obstacles to really making the leap from, let's say, lab to the reading room. So I'm wondering, in general, what are some barriers that you see to democratization of BERT for radiology tasks? Clearly there's some technical pieces as we talked about. How do we make sure that we train a model that can generalize, whether it's the regularization techniques during the model training or amassing a diverse data set, but also in sort of the kind of making the rubber meet the road with actually deploying it. So I'm wondering, we talked about a couple of them, but do any other major ones come to mind, in particular for any listeners out there who are interested in maybe trying to apply and deploy these algorithms in real time?
Right, certainly. I guess there's probably two prongs to the question. One is, what are some challenges and what are some ways to facilitate integration of these AI algorithms? And then the other prong of the question is, how do we make these models more easily generalizable in real clinical workflow, so that it doesn't just stay in the theoretical realm, but actually it gets integrated into actual clinical workflow. I would say for the first question, the difficulty oftentimes involves many regulatory steps. So there's governance piece of working with the senior leadership to try to move forward with these algorithms. And then there's also sometimes, even if there's full support from, say, the department or the hospital level, there may be already pre-existing players, sometimes commercial players in place. And if the algorithm perhaps runs in competition with the existing players, then may be problematic. In this case, because the ideal integration of the algorithm is actually with a dictation software and like the report itself, oftentimes it would be a commercial entity. And in these cases, it may need some negotiations or at least some talks with these companies. So I think those are some potential barriers. Second part about generalization of the algorithm or making sure the algorithm is more generalizable in clinical workflow. I would say, again, come back to the diversity of the data set would be really important. So if an algorithm is trained on multiple different institutions with a lot of different radiologists, for example, in this case, speaking in different manners and making different types of speech recognition errors, I think it'll only help to increase the generalizability of the algorithm. So there's different techniques out there. You can all pool the data sets together into one central pool data sets, which is very difficult in terms of regulations. Sometimes we can employ such as techniques like federated learning to share these weights and train together. These are some different steps. There's also some individual institution level techniques you can employ to increase generalizability as well. We talked about adding regularization to reduce overfitting. These are some various different strategies that I have in mind to try to make the model generalize.
I'll echo everything Jay said. One thing I'll just add is bias in NLP is a very real process, and it's not free from bias. And just like anything else you think for computer vision too, right? Medicine is a couple years behind, maybe a little more behind industry in terms of the technology we have. And so we've seen examples in industry, LP and transformer models, that unfortunately bias wasn't caught at upstream stages and at early stages and led to differences in gender. And I won't say too much here, but there are examples in the real world of where gender, race differences have manifested in the outcomes owing to upstream biases in the NLP pipeline that weren't addressed. And so when we think about medicine and we think about where bias in NLP can manifest, you think about as early as selecting that training corpora. What's the race and gender balance? Which languages are included? Is it purely English-based training set? When we talk about barriers to deploying it, that may not be a model that you can necessarily use in a non-English speaking or reporting nation or culture. And then you think about connotations, things that aren't said, but they might be implied in between the lines. Gender roles, emotive words, demographic information. And what's particularly interesting, and this is just off the top of my head, is public health associations, right? And maybe you all know about some resources that we can read up on, but what if models can learn public health associations from radiology reports? Maybe they can identify certain demographics are more prone to disease. And we start seeing a pattern that emerges similar to Dr. Gijoya's work and her team's work showing that race can be detected on chest radiographs, right, from computer vision models. But what would be the NLP analog? It's just answers that we probably need to start looking for in the future. As Jay said, annotating the data set can be an issue too, right? The experience of our annotators, the expert level, are we having interns and R1 residents annotating these reports, or are we having fellowship trained senior radiologists? What human biases are being conveyed? And then also, are developers even aware of potential semantic bias in data sets? Again, we're thinking about the NLP pipeline and thinking about where we can insert checkpoints and stops to catch it before it actually gets to the final stage. So bias in NLP, I think maybe it's a underexplored field. And I do predict that we will start seeing more about this as BERT starts to take off in radiology and we start actually seeing more real world deployed models and maybe some real world lessons that come from it as well.
Yeah, Ali, I think that's super interesting. Bias is clearly something that's unfortunately pervasive through many things in life, and machine learning, whether it's with computer vision or with text analysis, is no exception. Just a side note, my group is presenting a paper at SimC-MIMI that evaluated bias in chest X-ray classification models for NLP. And what's interesting is that, and maybe this is a positive thing, we didn't find any bias based on sex or by race, but we did find it based on age. Basically, a higher error rate in patients over the age of, say, 60 or 70. And initially, I was thinking, that's interesting, because I would like to think that as a radiologist, I'm aware of the age, I'm aware of the sex, but I would like to think it doesn't affect how I am treating the patient. My hypothesis is actually that, as you're saying, maybe there's some association. If you're older, your chest X-ray is not going to look as nice or as normal, and you're going to be describing things in a more convoluted fashion. You might be hedging a little more. You might be saying our technique is suboptimal. So I've actually thought that, it's interesting when we think about bias in machine learning. I think a lot of times, we personify AI as, oh, it's racist or it's sexist, but when in fact it may be in its behavior exhibiting those things, but in a way, it's just learning some of the maybe the artifacts of just the realities of disease. Let's say the older you get, the more disease you have. So yeah, it's just interesting to think about it in the context of text.
Absolutely. And, and this is, again, just being theoretical here, but I could easily imagine a model that starts to learn from reports in a way, artifact associated with, let's say, we've all seen good pulmonary embolism studies, and we've all seen bad pulmonary embolism studies for multiple reasons: motion, contrast timing, patient-related factors. But can you imagine a model that starts learning these artifacts and starts associating with BMI, for example? And all of a sudden, it's learning a similar association. Now, what that holds downstream, I'm not sure of, but I could imagine that warrants a discussion. And that's one example of just associations that we can start seeing as we start having more use cases take off. So, and that's great to hear about the CMIMI presentation. Definitely looking forward to that, Paul. Absolutely.
Yeah, very interesting discussion topic for sure too, because one observation we had from the model's error analysis was that certain grammatical errors that are really pervasive in radiology reports, to the point that we don't even call them grammatical errors anymore. I think one of them was just soft tissues unremarkable. And the model actually sees that as normal because it sees so many of these cases as normal. And this is a pretty benign case of just grammatical error. But if it was certain other important things, whether it be patient's age, gender, race, any of these things that are just occurring really commonly in certain reports, I can totally imagine the model learning that pattern, and then its output will reflect that result. So part of it, for sure, I think, is the issue with the data. And there's always some sort of bias, or one could argue that certain patterns are just present in the data sets. And as a artificial intelligence practitioner and as a doctor, I think if there's a way we can really have better grasp of this and understand that there's bias already present in the data sets, and have some good way of understanding how that may manifest in the model output, I think that'll really help us to become more mature practitioners of artificial intelligence and radiology in this space.
Yeah, I think I couldn't agree with you more, Jay. I think the more I learn about AI, the more I realize that I don't know. And I think if we extend that to our field, I think there's a lot of fundamental questions to ask before we can even begin to start unpeeling the layers of all these issues. So as we move into the last minutes of our time together, I want to ask you guys, as we look to the future, what are you most excited about for the next 10 years as you think about AI, whether it's NLP or computer vision and BERT or ELMA or whoever?
So 10 years, you think about 10 years ago from today, and it's such a different landscape. So I can only imagine, right, 10 years from now, how far off we would have taken in our field. And I think if I had to pick one, though, staying true to the topic of our session, I'd say using NLP, right, using these BERT and BERT derivative models for AI monitoring. I think that's a really high yield use case. There's definitely, we're seeing a transition to more interest in AI monitoring, looking at clinical performance, finding key performance indicators that actually reflect clinical outcomes. But it's still quite a bit of data to mine. It's a lot of data to keep track of. And we have business intelligence tools and dashboards to help us. But I think incorporating NLP as a baseline to, and specifically, I'd say transformer-based models to actually start extracting some information from reports to start looking at things like concordance, maybe even turnaround time, pairing that with outcomes. I think that's a really high yield use case that we're going to see more of, hopefully in the next 10 years. I'd hope in the next couple of years, but I think 10 years for sure. Jay, what about you?
Yeah, 10 years is a long time for sure. If you just think about 10 years ago, 2012, we would not even be talking. I'm not even sure if the term deep learning was coined at that time, 10 years ago. I think it was around 2014 or 15 when we were really, really sort of jumping into this field. So long time for sure, but I'm really, really excited about the future. And I'm also staying related to the session. I'm seeing more and more potential for integration between language and imaging. So what I mean by that is a combined modeling of both radiological images as well as language together to really understand what it is, what kind of pattern it is that we as radiologists are recognizing, and then also documenting in our reports and then communicating to physicians. So I think certain sort of preliminary steps are being taken. We know about the MOM model from Google and various other combination models. So I think an advantage of that type of model is that we will be able to say when we are dictating a radiology report and seeing an image, as we sort of partially dictate the report and pull up the images, we can perhaps query, these are the set of images that are very similar and related from a very large database. And you've written maybe half the report, and these reports, image pairs, are similar to perhaps 10 among these 10 million image report pair. And I think that's going to be a really important type of decision support tool that will work alongside us as radiologists. Going further, sort of related to that, would be a really tight integration of AI into our workflow. So in every aspect, from protocoling to generation of reports to maybe validating the report and seeing, how confident are we about this report? Now, after you finish your report, it's going to do its spell checks. And as you're about to sign the report, it's going to show you, here are the 10 similar reports that were written in this topic. Do you like the report? Knowing that there's 10 of these reports that are related to your reports. I think that'll be really, really convenient as radiologists. I still think we'll have a role to play in that world because there's always somebody who will need to check and make sure the report is headed in the right direction in the particular clinical context. And there's always unexpected errors being made by AI algorithms as well. But I think overall tight integration of artificial intelligence to our workflow and multiple modeling that combines the language and images. I think those two are topics that really excite me the most.
Drawing a that's really interesting. And that actually makes me think about a recent use case I read about in the non-medical world about BERT. And it's just to be really brief, essentially, this team compared a rules-based approach to BERT in terms of giving a quality score to basically Kickstarter funds, to GoFundMe entries. And then they essentially were looking for any relationship between the quality of the report as graded by these two NLP models and the success of the campaign. And so at the end of the day, they were basically using BERT to give it a quality report. Well, can you imagine a radiology report that has BERT saying, this is the quality rating is pretty poor on this report. You might want to think twice about this, right? I think I'd probably think twice about it, especially now that we have the Cures Act and patients can look at our reports and maybe there's some correlation there, right? Speaking of patients too, I think there's going to be a big role working on what's already being done in terms of making reports jargon-free, using NLP to help strip reports of jargon once it gets to the patient side and making it more understandable, more relatable for them. So I think we're going to start seeing is more of the patients actually entering these AI conversations. I think we're still at a point maybe where it's too early, right? Radiologists are still finding that nice balance of where AI fits in the workflow. But I really do think we're getting close to where patients will be part of that conversation. Now, that's a whole separate topic, but I think they're aware. And we as radiologists have a chance to take that role, step up, and really lead that information, dispersion of that information and how it's conveyed. So NLP, I think, will definitely have a big role in that, in making that connection.
Thanks for sharing all of those predictions and topics to look out for. I think maybe in short, we can say that our words matter. And so I think it's going to be really interesting to see how AI and NLP really affects that going forward. So I want to say thank you again, Ali and Jay, for joining us here on the Radiology Artificial Intelligence podcast. It's been a pleasure having you, and we appreciate your time.
Thank you.
Thanks for having us. It's been good.
Thanks for joining us for this episode of the Radiology Artificial Intelligence podcast.
Interested in learning more about NLP and BERT? Check out the latest articles at the Radiology AI website. Thank you to all our authors involved in these projects and for sharing this work with our field.
We hope that you've enjoyed this episode of the Radiology Artificial Intelligence podcast. Shout out to Uriah Shemchisen for our podcast music and to the RSNA podcast staff.
Email us at podcasts@rsna.org anytime with questions, feedback, or suggestions.